So let's continue, shall we? Thank you so much for coming back. We are moving on with Code Dive, and our next speaker is Maciej Norberciak. Now, Maciej works in Nokia primarily as a software architect, but he's also a trainer and a mentor. He holds a Ph.D. in computer science, specializing in artificial intelligence, but works in the telecommunication industry, taking part in various projects on various embedded platforms as a programmer, designer, architect, and project manager. Now, Maciej is a very experienced code diver, so experienced that today he's going to deliver 2 talks. The other one will be taking place at 5:20 p.m. in room number 9. Other than that, Maciej is here with us. So, software architecture patterns in 1 hour or less. Let's have a big hand for Maciej Norberciak.
All right, a word of disclaimer for those of you who have seen the previous talk. I will be talking about software architecture patterns, but there will be a short 5-minute introduction about software design patterns. Bear with me, it will be short and snappy. I hope you will be at least entertained. I have to admit that I have very limited experience with active job seeking, but I do enjoy reading an occasional job ad. They are constructed in a similar manner. We are company XYZ, we are producing stuff and thingies. And we are the market leader, we are looking for you for the position of Vice President of Water Surface in order to reap our albeit meager benefits. You need to possess certain skills and knowledge. And the skills and knowledge section is written in cryptic jargon full of abbreviations. Some of those abbreviations are eternal and will be with us for foreseeable future. And some of those are just fads and come and go out of fashion. One particular abbreviation was very popular in 1990s, late 1990s, early 2000s. You needed to know your GOF. GOF written like that or like that. You already should know that this is about Gang of Four, but not this Gang of Four, the original one. But Google them. Gang of Four China, and just imagine what kind of person you have to be in order to be considered an extreme leftist by a communist Maoist in China in 1970s. We don't call big tech Gang of Four anymore because apparently right now this is Big Five, although Facebook, Meta, is not even 5th but 7th when it comes to market capitalization. We are talking about that. As the title of this book is a mouthful and doesn't really roll good out of your tongue, that's why this politically incorrect nickname stuck. But the book was published in 1994 or 5, very successful, selling 500,000 physical copies of something in our industry is really an achievement. And what's a design pattern anyway? It's a battle-proven solution for commonly occurring problem. And though this problem has to be, occurring often enough to be easily generalizable, and on the other hand, the solution should be general enough to be applicable in a variety of contexts. And this application comes during, design process. And I don't want to get into terminology battle, because if you Google what's design in software engineering, you will get a number of results and every single one will be different. For the sake of this talk and risking oversimplification, I will say that design, when we are talking about design, we are talking about object-oriented design, so class/object level. We are doing design in software engineering and then implement the systems in languages that do not support object-oriented paradigm. But again, for the sake of simplicity and for the sake of this talk, let's keep it to the class and object level. Conveniently enough, design patterns are given to you in the form of textual description and, class diagrams like this one for observer pattern. But I'm not here to talk about the software design patterns, but rather software architecture patterns or styles. I will be using the name style and pattern interchangeably, although there are some authors that believe those are two different things. I'm not one of them. Again, I don't want to get into this eternal struggle. If you Google design versus architecture software engineering, on the first Google search page, you will get 10 results, 10 different results, 10 vastly different results. But we will keep it simple here. If I am saying that design is on a class and object level, I will be saying that architecture is one level higher, on a component level. And components are comprised of classes. Each component is a building block of our application, our system. Each component has a certain set of functionalities, roles, responsibilities assigned to it. And we group components in even larger grain architectural entities. We call them subsystems or layers or services or event processors or whatnot. I also will be using term module interchangeably with components. Technically, module is a collection of related code, and in different programming languages we have different facilities that allow us to provide physical packaging for the module, like, I know, jars in Java, or I think there are X in Python and gems in Ruby, that kind of stuff. All right. With that introduction and terminology part out of hand, we can go to our first architecture pattern. And this first architecture pattern is the monolith. This is super ancient. It's like 70 years old. This is the first software architecture pattern invented, before even we called them software architecture patterns, and all monoliths are pretty and shiny from the outside. But in our industry, it's the inside that matters, and not all monoliths are created equal. Basically, we have two kinds of monoliths, unstructured and structured ones. Unstructured monolith is a collection of tightly coupled classes. Coupling is a quality measure. To keep it simple, it's a measure of interdependency between entities. You can measure it on the class level, you can measure it on the component level. Basically, if your class, if your component needs another entity to function, those two entities are coupled. And as designers, as software architects, we aim for low coupling because it makes our maintainability higher. In this case, we have, well, independent classes doing independent work, that is good, but also we have common classes that are doing common work. And what unstructured monolith really lacks is, well, the structure. Lack of overarching structure hinders the ability of this architecture to change. That means that the change becomes difficult, and when someone like me, a software architect, says you that something is difficult, that means that this is costly. But this is not like design patterns that Brandon listed 20 of them and then crossed half of them out. No, we still do unstructured monolith. You can do unstructured monolith too if you are one guy, if you are tight on budget, if your application is small, like 30,000 lines of code. This is something one person can comprehend easily. If you do an experiment, one-off thing that you know that you won't be maintaining anymore, unstructured monolith is fine. Otherwise, you would like to have something with, well, more structure, a structured monolith. In structured monoliths, we try to segment code into components. And each component has roles and responsibilities assigned, and each component provides you with an interaction point to cooperate with other components. Those interaction points, those APIs, interfaces, are where the devil in the details hides. You should keep your interfaces stable. That means that if you change the implementation behind the interface, the implementation of the component that provides this interface, the definition of the interface itself should not change much. Also, you should keep your data isolated. So if your component requires some data set in order to perform its function, this data set should be available for this component and this component alone, maybe embedded in this component, not shared promiscuously throughout the system. So if you keep your components if you keep your interfaces stable, and if you keep your data isolated, you are on a good way to provide pretty decent architecture with low coupling and high internal cohesion. Cohesion is also a quality measure, like decoupling, twin to coupling, I would say. Coupling is on the outside, and cohesion is internal. If your entity, your class or your component has just the things inside that do one thing and one thing only, provide one functionality, one responsibility. Remember solid principles from Uncle Bob. That means that your class or your component are internally cohesive. And as designers, we aim for low coupling, high internal cohesion. Okay, so you may ask yourself, why not stay in monolith world? I've shown you one architectural pattern that, well, has its uses. And another one that I said that is pretty decent and can give you a good architecture. Why? What I'll be talking about for the next 30 minutes or so. And obviously, those other patterns I will be talking about do something better. But what's this better, and why haven't we invented better in the first place, you may ask? Well, the answer for that is historical context. You see, architectural patterns are like art movements. They have to be considered in the context of an era they have appeared in. And the context for monoliths was that this was not only architectural style. This was also a deployment model, a monolithic deployment, a unitary deployment. So you have your garden variety mainframe, one machine, and one program that runs on it. No networking, no distribution whatsoever. Gradually, as the capabilities of computer systems grown, we separated some stuff away. First, we separated hardware from the software, but then we separated data away. First, mainframes moved the data to another hardware and another software to a database server, for example. In order to have something more in terms of software architecture patterns, we needed a push, evolutionary pressure, so to speak, because also in the world of desktop PCs, okay, we have our second technical glitch. Oh. Can someone please help me? I think it hung completely. Zawiesił się. Okay, but desktop PCs, as they appeared, also much of the development was focused on unitary deployment. So you have your PC, you have a program or programs that run just on this PC, just on this PC alone. And this evolutionary push that appeared after a while was distributed computing. But it's not like it appeared out of thin air. We needed to... we needed some time to arrive to distributed computing. And it started with the birth of the terminal. Let's take a step back to 1959. You have $20 million spare and you buy a sophisticated IBM machine. It's a couple of units. You bring your program on punch cards to one unit. Then this unit translates it into a magnetic tape. You take this tape to another unit that does the actual computation. You may argue that this is already a distributed deployment because you have two machines and you move the data through a networking protocol which uses physical layer and transport layer in the form of human carrier. So yeah, distributed deployment, why I'm talking about the monolithic one. Well, pretty soon we merged those three machines together. You still needed to bring your punch cards to the machine. and you needed sort of sophisticated typewriter to provide those punch cards. So the next step was to put this typewriter onto the machine itself. So you can program the machine interactively. That was a dumb move because your mainframe produced a lot of heat and it was noisy. So the next logical step in evolution was taking this typewriter away from the mainframe again, but it was connected by a cable. That was the birth of teletype. So the first terminal, but it was just the keyboard at first. Just the keyboard, and it provided a hard copy on your punch cards for future use. In order to have real interactivity, we needed a feedback from your machine. Of course, it had some lamps that blinked in another room. You needed to see those lamps, so we put a CRT display on this keyboard, and thus the glass teletype, glass TTY, or a terminal was born. At first, it looked like your garden variety PC, but it was not a personal computer per se. It had no CPU, just low scale of integration components. It took some time to develop into a PC. But first step was made. You had a user interface on the terminal and the machine that did something remotely. But before, okay? Thank you very much. I will treat you to some fast pictures now. So yeah, this is this IBM machine I was talking about, the glorified typewriter, first teletype, and the glass terminal. This is 1964, I think. Okay, the problem was that this thingy sent whooping 15 characters per second to the mainframe. No human can type that fast. That means that your multi-million-dollar investments are sitting idle most of the time. So in 1970s came a revolution. We put a bunch of those terminals connected to one mainframe, and it did some clever switching to give the users illusion of exclusivity. This was called time sharing. And one step further was actual distributed computing. Because as the user interfaces on those terminals grow more sophisticated, the capabilities of the terminals grown more sophisticated, and the terminals grown into desktop PCs. And we invented another software architecture pattern, which is called two-tier architecture or client-server architecture. Again, it's not like we invented it in 70s and then dropped it because you invented something else. No, this first use case, UI terminal plus database connected remotely through a set of standard networking protocol was just the first step. We did it again when we started doing World Wide Web. We have a thin client, the browser on your PC, it connects to a web server. But you may argue that this web server actually probably has some database connection too. So this is not really two-tier, but maybe 2+, maybe 3. Well, yes, it is. But before we go to that, let me make a slight digression about the origin of names of all those patterns that I have described and all those, the patterns that will follow. We don't have a secret society of architects that are meeting in the middle of the night and scheming what the next big thing will be and how we will call it. No, most of software architecture patterns are named after the fact. So the software development ecosystem changes all the time. The capabilities grow, and we have to respond to these changes. We need to make decisions that allow us to exploit those changes, profit from them. And as many software architects make same decisions and other architects emulate those decisions. Someone finally notices that, hey, we have a new pattern emerging, let's call it XYZ. So no secret societies whatsoever. I'm not a member of one. We don't get magical tattoos on our backs. Coming back to our three-tier architecture, yes, this is a thing very popular in 1990s. You have a front end separated from the back end. Front end connects to application server connects to the database server. In 1990s, it was supported by technologies like DCOM and Corba. If you are born in 1990s, you probably never heard of Corba. But it's, again, not like this architecture is dead because it peaked in 1990s. No, this is still very much alive. If you Google Amazon Web Services, the first diagram that will appear will be that. Three-tier architecture proper. Okay, so what would be the next step in evolution? First, we need to make some name changes. We will call those tiers layers. So we have a presentation layer, application layer, database layer. Each layer is comprised of components. Each component has a defined set of roles and responsibilities, and if component is in one particular layer, it does the task connected to that layer and that layer alone. So the presentation layer component, for example, does just the presentation thingies. This is called separation of concerns. And it's actually very convenient for organizations that do provide software, that sell software, because they can focus their development focus into particular areas. I'm the database guy, I do only databases. I have colleagues that do presentation, I have colleagues that do application, but we just communicate through interfaces. Very convenient, very easy to manage, and, well, maybe not very easy, but easier to manage such organizations, such products. The next logical step in evolution would be adding more layers. There is no restriction on how many layers you need. Typically, there are 4, called like that, but if your application is smaller, you may have less layers. If your application is bigger, you may have more layers, 5, 7 even. And this is called layered architecture or n-tiered architecture if you really like these tiers and not layers. This is a natural architecture. If your agile team just starts coding, there is a good chance that you will end up with something like that. That or big ball of mud, actually. But even before agile world, when we worked in waterfall, this fit quite nicely into the structure of organizations that provided the software. So you have the presentation guys, you have business guys, you have database guys, and so on. This is the embodiment of Conway's law. Melvin Conway was a guy that in 1957, on one of the software development conferences, and believe me, there were code lies like that already in 1957, he made this remark that organizations that provide software, they tend to mirror their organizational structure into the structure of the software. They tend to mirror their communication paths into the interfaces. And this was so true. And it's still true that we are now calling this Conway's law. So if you have an organization structure which is a layered one, you naturally provide layered architectures. Your layers can be opened or closed. When you have closed layers, and for example, want to show something from the database on the presentation layer, your call has to go all the way down through all the layers. This costs sometimes a little bit performance, so for this particular case, we invented something called fast lane reader pattern. So you call the database from the presentation directly, thus making your business and persistent layers open in this example. What style is better? Well, I cannot tell you because it depends. In closed layers, you lose a little bit of performance. In open layers, you gain performance, but you lose maintainability because you can't implement layers of isolation. This is a concept that there is a contract between two layers. And if your layers are closed and you change one of the layers, you potentially influence just the contract between you and the layer directly above or below you. In the case of this example, if you change database layer and your layers are opened, you not only potentially influence persistence layer, but also the presentation layer. Your maintainability is lower. But again, it depends. Every single architecture decision is a trade-off. Before we go further this evolutionary path of software architecture patterns, let's look at things that are not necessarily databases. Pretty soon, we, the software developers, realize that if we have one big task, we can split it into smaller ones and pass the data from one task to another in a manner that you should already know from Linux command line. This resembles a pipeline. And here the pipeline architecture takes its name from. So this architecture is also called pipes and filters architecture because the topology elements are called pipes and filters. Filters come in 4 shapes and sizes. First one is producer. It starts the flow. It produces, fetches the initial data set. The consumer consumes the result of the flow, for example, by presenting it on a presentation on a terminal. Filters are connected together with pipes. Pipes are usually unidirectional, point-to-point elements. They pass the data. And the filters that do the actual job here are called transformer. So transformer takes the data from inbound pipe, transforms it somehow, and puts the result into outbound pipe. And the tester takes the data from inbound pipe, and depending on the result of some test, may put the result into outbound pipe. And as we go through the entire pipeline, the consumer finally produces the result of this flow. Very convenient architecture if you have something to do in a synchronous manner, deterministic. Again, still very much in use. Service orchestrators like Apache Camel do this kind of architecture in order to pass data from one stage of business process to another. But sometimes you need something more than a pipeline. You need branches, you need asynchronous reaction, you need to handle some stochastic process, you need actually a network of pipes. And this straightforward path through the pipeline is not enough for you. That's why we invented event-driven architecture. It's from layered architecture on, all those architectures can be distributed because you can distribute the topology elements of those architectures in any manner you would like. In layered architecture, you can deploy all the layers as a unitary deployment on one machine, but you can distribute them and communicate through the network. Event-driven architectures come in 2 types, mediator-based and broker-based. Mediator is a central element that controls the entire flow. In mediator, we have no central control. We start with that. We have an initiating event. A broker, usually some lightweight thingy right now, like RabbitMQ or ZeroMQ or something like that. And we have a number of event processors. So the event, the initiating event, comes to the broker, and it's put in the event channel or registered to a topic. Those event processors that are interested, subscribed to this topic, get the event and can process it. Sometimes producing some intermediate result, a processing event that comes back to the broker and is put in appropriate topic, and the event processors that are potentially subscribed to this topic get notified, can do the processing. Those event processors may either be stateless or data dependent, so they have their own isolated data set. This is quite good, quite performant if you have to react on events in an asynchronous manner. But if your flow is complicated or you need central control, you will go not with the broker, but with mediator. Again, we have event. Event comes to the mediator, it is put in the queue. And mediator takes event from the queue, examines it, and depending on the type of the event, it notifies the event processors. For each type of event processor, we have a separate event channel. They process it, and if they produce an intermediate result, a processing event, it comes back to the mediator, it comes back to the queue. Again, I cannot tell which style of the event-driven architecture is better, mediator or broker, because this depends on your use case. But usually, if you have a complicated flow, you go with a mediator. Of course, this is a simple view on this architectural style. You can have multiple mediators. Everything can be distributed. All right, so this is the end of this evolutionary path from the pipeline to event-driven architectures. The last evolutionary path should be known for all of you. Okay, let's have a quick show of hands. Who uses Visual Studio Code for development? Oh, a lot of people. Okay, anyone uses Eclipse? Oh, one guy. Sorry, the lights are very bright. Vim, Notepad++. Oh, Vim, Notepad++. Yeah. Okay, you are hardcore. All those applications have one thing in common, and this thing is architectural style they are written in. We have a core system that doesn't really do much, and the number of plugins that provide the real business value that you use. And because of plugins, this is called plugin architecture. You may also know this as microkernel architecture. This core system, in case of Eclipse or Visual Studio Code, is just a glorified text editor. You can edit the file, save it, load it, do some editing, but that's all. This is so-called happy path through the application, minimal functionality to run the system. There may be an optional presentation layer inside, but not necessarily. This can be provided also by a plugin. And in order to have the awareness about the plugins connected to it, the core system always implements some kind of plugin registry. And the plugins are the thing that really do the hard work. They are standalone and independent. Well, not in the sense that you can deploy plugin independently of the core system, but they are enhancing the capabilities of the core system. They communicate with the core system in a point-to-point fashion, and they can be either local or remote. So again, this is potentially a distributed architecture. And those plugins can either be compile-based or runtime-based. So if you have a runtime-based plugin architecture, you can plug things in and out without influencing the rest of the system. If you have compile-based plugins, you have to at least press the reset button. Multiple things, not only the IDEs, things like Jenkins, Jira are also plugin-based, and of course, all those architectures can be hybridized. You can have a monolithic plugin, you can have a layered plugin, your core may be event-oriented architecture. This is pretty elastic. Okay, I've mentioned a couple of times things like maintainability, deployability, scalability, and so on. Those are called architectural characteristics or quality attributes. You may know those as non-functional requirements, although I don't really like this name from various reasons. You have to optimize them. You need to keep your system, for example, secure and scalable, but this is one-off thing, so you don't need maintainability. The problem is that you can't optimize them all at the same time, because their name is legion, for they are many. They are sometimes called ETs because most of those names end with ET. In big systems, we want to have different architectural characteristics optimized for different parts of the system. But how to do it? First, you need to know where those architectural characteristics actually live. And now there will be a hard part because they live on the quantum level. Well, this is not actually that hard because we define architectural quantum as an independently deployable component with high internal cohesion. And there is one more thing that is very important. Architectural quantum must include all the elements that are needed for the system to work properly. So you deploy one quantum, you may have many quanta, but if you deploy just one, you already have some little system that provides you with some functionality. And further evolution of architectural patterns is based on the fact that we want to have more architectural quanta, so we can optimize architectural characteristics for each quantum independently. Okay, so let's take our layered architecture. Let's meet in the night and scheme. Let's paint it blue, call it user interface, and we will paint it red and call it service. And then we will split service layer into separate services, thus creating service-based architecture. Those services are called macroservices or domain services. This is some part of the functionality of the system. You have a user interface, a number of services. They are all using the same central database. How many quanta we have here? Well, I would argue that this is still one, so what's the point? How to create more architectural quanta? Actually, the idea is pretty simple and comes from 1970s. Let's separate the data away. Short example, you have a web shop, you have customer-facing services, in this case just one, this on the left, order service, and you have vendor-facing services, so those on the right, sales and inventory service. You provide separate UIs for them, so you have internal UI for the vendor and public UI for the user. And then you separate data too. So public UI with order service has some small data set that is enough to function properly without the connection to the rest of the system, which has its own database. Of course, they need to be synchronized from time to time. But essentially, we can deploy those two parts independently, and they can work independently, at least for some time before this synchronization is absolutely vital. And each of those parts will be a separate architectural quantum. So we can manipulate architectural characteristics of each quantum separately. You see what we did here? This is a very simple decoupling technique. We took a big macro service-based system, and we split the UI, which is probably very easy because it's probably some thin client, even a web browser, so there is not much splitting to be done, and we separated the data. And that was the big idea, because we, instead of one big quantum, we have right now two quanta. Lowering quantum size, individual quantum size, was the key to the last software architecture pattern that I will show today. This is pretty widely known because all the hype is right now on microservices. So we take our macroservice, a big one, and make it smaller. But microservice is not a commandment, it's just a description. The fact that you have this low granularity in your services doesn't necessarily mean that you have microservices-based architecture. Now, in order to have real microservices, you need to separate, decouple your data too. So each and every individual microservice has its own dataset. It's called bound context. And this bound context contains all the data this particular individual service needs to function properly. So you can deploy just one service and you already have functional system. Of course, the functionality is minimal because your services are small. But you already have a system. So each and every service is a separate architectural quantum. Of course, you need some API to access services, and you have to handle the client requests from APIs. But the key is that your services are quite small. And this is actually the only architectural pattern I know of that was not named after the fact. Actually, Martin Fowler jumped the gun in 2014 when he wrote a blog post called Microservices, and he said that, hey, look, we have a new pattern that has not emerged, but is emerging, and is a fine one, so use it. Yeah, we asked him to remove his magical tattoo after being trigger happy. Okay, before we go to Q&A, I will take the liberty of answering one frequently asked question by myself. What is the right architectural style for your system, for your application? I would really like to give you a straight answer, like you can be whatever you want to be, unless you can be Batman, then be Batman. Certainly, in software architecture, fashion is a thing, and microservices at some point were all the hype, and everyone wanted to do microservices no matter what, whether it made sense or not. Also, we learned from the past, no one starts developing the application with this idea in mind that this will for sure be a monolith. No, but software development ecosystem changes all the time. The capabilities of computer systems change all the time. The business changes, the tech changes, and those changes are faster and faster. So unfortunately, for this question, I can offer only one answer that is an answer for every single interesting or difficult question, and the answer is it depends. Now, a bit of shameless self-promotion. If you want to know on what it depends and maybe how we architects make these difficult decisions, I will have another talk later today. This will be about the path from developer to software architect, but I will also tell much more about the software architecture as a discipline and how we do all those extremely difficult tasks. Thank you very much for attention. Let's have a Q&A.
Maciej Norberciak, thank you very much. I think we just have several minutes for questions, if you've got one. I know that the cleverest answer ever is it depends, but maybe something more elaborate. So anybody, please raise your hand and we'll run to you with a mic. Any questions about patterns? There's the one over there, so can we have the mic there, please? Thank you. We're practicing running the stairs beforehand, but maybe not fast enough.
Can you show that secret tattoo that you don't have?
I don't have any tattoo and I'm not a member of any societies.
Thank you. Wonderful question. There is one over there, please. Thank you.
Okay, thanks. That's conveniently a thing that a member of secret society would say, probably. My question is, because I get a feeling that the progress of the architectures that you have described was from worse to the better, although you have concluded that there is not a silver bullet in there. But my question is about the family of the ITs that you can cover by testability. And I was wondering about your impressions, whether going from monolith to micro architectures or even the middle layers, how do they affect the testability? Because in my opinion, the monoliths have this advantage of being easily testable at a lower level. So you can write a bunch of unit tests. And I wonder, what's your experience going to the microservices? Is the testing easier or harder? Because I think you need to switch from unit tests to integration tests, and those are harder to write. So you need to test the contracts between the architectures rather than the monolithic layer that the user says. I'm not sure if that makes sense, and I hope you get the spirit of the question.
I get it. Well,
thank you.
It depends. Sorry about that. I see no problem with making a unit tests on both architectures, because in the end you do unit tests on the individual pieces of code, classes or components or something like that. In case of monolith, your components provide you with a set of interfaces, you test around those interfaces. In case of microservices are comprised of components. You do unit tests on those components. Inside those components, you have classes. You do your tests on the level of classes. So I would say that the stability of microservices is a little bit better, because you can test individual services still in the manner like the unit test, but this will be a sort of integration test already. So yeah, it really depends.
Thank you. Any more questions, please, anyone? Yes, there's just one over there, please. And another one here. Okay.
Hello, another Maciej here. So I have a question about the microservices, and I was just wondering, because it sounds like a sort of good approach to certain problems I have, and I was just wondering about this, what is called bound contexts, meaning how do you really synchronize the data? So it's like, do you have some assumptions that there's some data which is, for example, always constant, or you have to provide another microservice, whatnot, to sort of have access to the same or rather all data to sort of have everything synchronized. So how does it work?
Okay, I should.
Maybe it's just sort of out of the context of this whole talk. So
No. It is very much in the context. The problem is that I had only 45 minutes, so naturally I skimmed the surface of the problems, because either I would talk just about microservices for 1 hour or so, or go through numerous software architecture patterns. To keep it simple and try to answer this question. Service granularity, synchronization, data synchronization, duplication, replication in microservices architecture is a thing. It's a challenge. And if you take any decent software architecture book on microservices, you will have 20 pages on each and every of these problems alone. And I cannot give you a simple answer, so, apart from, of course, it depends. But yes, those are all challenges, and yeah, I would probably needed an hour or so to just enumerate the ways we can handle it. Yeah, so I'm sorry if you don't get enough information from my talk, but for the sake of simplicity and brevity, this is how it is. But it is a challenge. It's not microservice architecture. It's not a silver bullet for everything. People, because of much hype associated with this architecture when it started to emerge, all people wanted to do microservices, whether it made sense or not. It's the maintainability, scalability, deployability of this architecture is very high. But the cost, the level of complication involved is also very high. So again, this is a trade-off.
One question over there, please.
Yeah, hello. What is the new what is the new pattern that is coming for us? The next microservices are now. What is the new pattern? If you will be trigger happy to name it, maybe.
I have absolutely no idea. I'm trying to keep up with what's happening in tech, but no one, since Martin Fowler did this article in 2014, no one has jumped the gun and said that, hey, we have a new pattern. I have to confess that I'm sitting in a very peculiar world of embedded systems, and we usually get those new exciting things 20 years later after they appear. So, to be honest, I don't know. Haven't seen anything that revolutionary like microservices in past few years.
Thank you. I think we have time for just one more. There's one over there just across the room, please. Maybe it'll be faster for me to walk there. So, just one final question.
Hi, I got a question regarding the popularity of the microservices, and to be honest, I have the impression that the one of the big reasons why it's so popular is because it's it better reflects the company or organization, that because it's more let's say I don't like this word agile, because it's easier to split the teams and to manage the whole. Because even if you try to be agile and you have monolithic architecture, usually you end with waterfall, let's be honest. And with microservice, you can actually apply this and split. You still have the dependencies, but it's not as tight coupled, let's say. And I think it's not a better architecture, but it's better reflects it's easier for managing, to be agile, and to be all this modern, let's say. And what do you think about that?
Certainly, the agility is yet another architectural characteristic or quality attribute or non-functional requirement, and sure, the level of this characteristic for microservices is quite high, but I cannot really tell the one reason why this has become so popular. You probably are aware of the hype cycle, that at some point everyone wants to do one thing, and then there is this disenchantment, and we go to the plateau of productivity. Okay, I would say something that is kind of obvious, but there is a sense to do microservices if it makes sense for your company and for your project, and there is no sense when it doesn't make sense. Simply.
Final question, final answer. Ladies, gentlemen, and everybody in between. Maciej Norberciak.